Hello, my name is John Bellardo. I'm the director of Cal Poly's CubeSat lab, located at California Polytechnic State University in San Luis Obispo, California. Today I'm going to talk to you about ISX, specifically about a failure analysis that we performed when we were not able to make contact with the spacecraft after it was launched. So before I dive into the failure analysis aspect, I'd like to give you a little bit of background on the ISX mission itself. ISX is a funded collaboration between Cal Poly and SRI. Cal Poly provided the bus, built the bus with our team of undergraduates and master students, and we were operating the spacecraft as well. SRI provided the science analysis and the science payload that was integrated into ISX, and it was funded through the National Science Foundation. The primary mission for the Ionospheric Scintillation eXplorer is to better understand the equatorial spread F ionospheric irregularities. The reason this is important is because these irregularities can severely degrade the performance of communication and navigation assets. So this is a space weather satellite that will help us hopefully predict and better understand these phenomena so we can use the other assets up there that we have. The way ISX was intended to work is a spacecraft will fly over major equatorial cities. As it's flying over the cities, it's going to do an observation campaign using the digital TV broadcasts that are originated from the ground. You'll recall that there's a transition from analog to digital TV a number of years ago, and then so those are the signals that we are leveraging. This means that we only need a passive radio receiver on board the spacecraft, so we don't actually have a powerful radar or powerful radio source on the spacecraft itself. We use the ground-based digital TV broadcasts, and we analyze how they interact with the atmosphere. So during our observation campaign, we save the data. Usually it's relatively short, 10 or so minutes. And then afterwards, we analyze the data. And that could take many hours to analyze the data to come up with the science result. Both the data collection and the analysis take a lot of power, and so we have to go many orbits to recharge our batteries before we can take another observation. Sort of the mission and ConOps in a nutshell. I want to talk a little bit about the spacecraft itself. So it's a 3U spacecraft based on a tightly integrated avionics and bus that we've developed at Cal Poly and flown many times over the last 10 to 12 years. Here you can see a drawing of the spacecraft with the major components indicated. I just want to draw your attention to a few here. Here you go. Very top of the stack, we have our system board and Z combination. This is where all the flight avionics are. So the flight computer, the flight radio, there's a GPS board, the communications antenna, the communications radio. And up there at the end of the spacecraft, you can see the battery pack depicted here in the middle of the spacecraft. And in the ISX model here, we have our payload and payload antennas down at the bottom of the spacecraft. That's the general internal layout of ISX. A little bit more detail about the avionics. They're based on a low power embedded ARM microprocessor we've been using for a number of years running Linux. There's about 8 gigabytes of onboard storage available via an SD card. There's additional couple hundred megabytes of storage via NAND as well. There's a UHF radio that was designed in-house that was we operated at 9600 bits per second, although has the ability to operate at other speeds as well. There's an integrated electric power subsystem on the single board, so we don't have a separate board for all our regulators, for instance. In addition, we had to make a few customizations for ISX. There's a custom interface adapter that connects to the avionics board and then provides the correct breakout and electrical connections for the ISX payload. We also had to add an adapter to run the system at sort of 12.3 volt nominal instead of our standard 4.1. ISX doesn't have any active attitude control. Instead, we passively stabilized it using magnets and hysteresis material. We did include attitude determination, so we had some idea about where we were pointing when we were collecting our data. Um, the attitude determination is relatively coarse, and the sensors that generate the determination are 6 solar angle sensors, 6 magnetometers. We also use the GPS for position and time information. As I mentioned before, SRI provided the payload. The payload consists of a few different components. There's a custom software-defined radio and RF front end to observe the digital TV signals while we're taking our observations. This was in turn tied to high-speed, high-capacity solid-state storage. Each observation generated gigabytes worth of data, so a very large data set at a very high rate. And it was decided there was not enough bandwidth to take that data and be able to save it to the SD card and the avionics. So there's separate storage and separate processing for the science payload. In addition to that, I said during the ConOps, we post-process the data. So the data gets post-processed on a NVIDIA Tegra-based CPU that is also running Linux. Both the RF front end and the payload processor consume a substantial amount of power, so they're not on all the time. They're just on when we're either collecting the data or when we're analyzing the data. ISX was manifested and launched on the Alana 19 mission on December 16th of 2008. This was on a Rocket Lab's Electron 4 rocket that flew out of New Zealand. The spacecraft was successfully deployed into a 500-kilometer orbit that was nearly sun-synchronous. The successful deployment was confirmed via a couple different mechanisms. First, there's feedback from the deployers on the rocket. Secondly, the tracking data that was made available by the 18th indicated that the appropriate number of objects had deployed from the spacecraft. So we were able to confirm that we had a successful deployment. Unfortunately, this is where the big anomaly happened that triggered our investigation. Unfortunately, we were never able to make contact with the spacecraft. We tried for many months to contact the spacecraft, both passively listening to it and actively trying to command it, to no avail. That didn't work out. And so we transitioned our effort from focusing on operations to more trying to understand what went wrong. So to help us understand the anomaly, we went through a fault tree analysis process. We had 3 top-level modes that we considered. Failure modes related to material failures, modes related to electrical failures, modes related to software failures. Each one of these high-level modes was broken down in many potential causes, and we went through and systematically discussed, evidence that we had from tests on the flight unit, from tests on the engineering unit, from analysis of the circuits and analysis of the structures. Went through and looked at all that evidence to try to decide if a particular potential cause was likely or unlikely to, have caused the overall anomaly. As you can probably imagine, since we didn't have two-way communication with the spacecraft, it was very hard to get data and close out a lot of the items that we came up with, so we weren't able to pinpoint, one or two things that were the most likely cause. However, I still think it's useful to share with the community some of the elements that we looked at as part of our analysis and some of the conclusions that we were able to draw. The first potential failure cause that we looked at was related to the failure of a trace on our system board. Right, so we observed during our ground testing campaign that there was an intermittent power on issue after one of our TVAC tests. The issue would manifest itself in the form of pressure. If you pushed on the circuit board in the correct spot, you could get it to turn on, and when you released the pressure, it would turn off. After some troubleshooting, we decided that the cause for this was one of the traces actually got damaged during the thermal cycling in TVAC, and it was no longer conducting electricity like it was supposed to. As a result, we applied a wire mod to the spacecraft. You can see the wire mod pictured here on the right hand side, the 2 orange wires that run between opposite sides of the board. That wire mod basically bypassed the damaged trace. So it's possible, one of the items that we considered was that this wire mod had failed when, during the launch environment or sometime between integration and deployment. The evidence we have that makes it less likely that this was a problem is that we were following our normal staking and wire modding procedures. So if you look at the picture, you can see where there's some staking on the wires. The wires are already low mass to begin with, but then we added staking to them to help remove the strain of the vibrations environment. So the chances that they physically separated from the solder joints or physically broke as a result of the launch environment are fairly low. Another thing that we considered was an antenna deployment failure. Unfortunately, we had an antenna deployment failure, I want to say 2 or 3 years ago on a different mission named ExoCube. We were lucky in that we could still talk to the spacecraft and actually confirm it was an antenna deployment failure. And so we have a really good idea about why that one failed. And so, of course, one of the first things that comes to mind is, well, golly, the antenna failed to deploy again. However, there's a lot of evidence that makes that less likely. The first thing is that we decided to redesign the entire antenna deployment mechanism. After the ExoCube failure, you can see a picture of the new mechanism here on the right. It's a lot more robust. It has gone through, hundreds of deployment test cycles, both in lab and in a relevant environment, and it has flight heritage on a couple of missions prior to ISX. So even though it's a possibility, we feel that it's not a strong possibility. Another failure related to that is a failure of the burn resistors. If you look in the right-hand portion of the image, you see two resistors. We run a lot of current through those resistors to heat them up. In fact, we heat them outside of the design spec, and that causes the tie-down wire to melt and the antennas to actually deploy. Every time we do that, it internally damages the resistors, and we found that they can only be used for 2 or 3 deployments before they just won't heat up enough anymore. So, one possibility is that we had damaged the resistors so much that that they weren't able to function. The evidence refuting that, however, is that we have procedures and safety mechanisms in place such that we always fly with a new set of resistors, so it should have never been burned before, and the safety mechanisms prevent us from accidentally burning and damaging the resistors while we're handling and testing on the ground. Another potential failure is that the spacecraft just didn't have enough voltage in the battery pack in order to boot up. We felt it was important to investigate this failure mode because we went back and there was a window when we could recharge the spacecraft, recharge ISX, prior to launch. It had been integrated in the dispenser for about 7 months, and then due to various schedule delays, we were allowed back in after 7 months to recharge it, approximately a month or two before it launched. When we came back and recharged it, the batteries were totally dead. It didn't have enough voltage to boot. So in that 7-month period, the battery managed to drain itself. So there was some concern that maybe that happened again, and when we deployed, the spacecraft battery voltage was too low to boot. However, there was a couple things. First, we were only in there 2 months instead of 7, so it shouldn't have, in theory, shouldn't have discharged in 2 months. And second off, the solar panels on the spacecraft should have recharged the battery. So it would have ended up having to be multiple failures that cascaded together, with the battery being drained and all the solar panels not working, or the EPS failing. Again, so we felt that the combination of those multiple failures was less likely. Now, the last item I wanted to highlight during this talk was a timing error in our UHF radio. So we use a half duplex UHF radio, and part of that circuit switches between the transmit and the receive chain. So there's a software timer that says when to switch to transmit mode, when to switch to receive mode. If for some reason that timer's off, you can get RF energy that reflects back into the amplifier on the radio that can end up blowing out the amplifier. We observed amplifiers blowing during our ground testing and development process, and we suspected it was timing related. We went and updated the timers in software, After that, we didn't observe any more amplifiers being blown. So obviously the flight software version for ISX included those timing changes. However, we're just there is no way to rigorously test it and reproduce it. So it's possible that the timer update was still insufficient, even though we didn't observe any more failures on the ground. So I'd like to wrap up with a couple of observations. Right, first is the obvious point that the fault tree analysis didn't identify one probable cause. We were able to go through and address and talk about a bunch of possible causes, and then provide evidence to refute it and evidence to support it, but we weren't able to narrow it down to one or two specific causes. But there are a couple of valuable lessons that were re-emphasized to us as part of the analysis process. The first is you always want to test your spacecraft well beyond what your launch vehicle requirements are. We did some of that with our functional TVAC testing, which identified one of our problems on the ground, but we could have done a lot more rigorous testing, especially around the battery state of charge issue that came up during the integration process, for instance. The other thing you want to do is always have good documentation when you're going back and trying to piece together what happened 6 months ago or 12 months ago, and you don't have information about the very specific details that went into the test and the very specific test environment. It makes it very difficult to understand, concretely what happened. So the documentation is not only to prove to the reviewer who's going to look at it in 2 weeks or 4 weeks that you met the test requirements. You want to have enough documentation so that when you go back and look at it 6 months, 18 months later, and it's a whole different set of people trying to do the analysis, that they have the information that they need to do their job. Okay, that concludes my presentation. Thank you very much for watching. If you have any questions, please feel free to reach out to me via email.